graph neural operator, if you have a very weird numerical solver, which means that you sample a very random nodes and connect them. If your numerical solver like that, the neural grapher can take that as input because it doesn't depending on the grid topological structure. Well, that's their clarification. You see in this picture, I think the blue picture is the solution of U. I think I suppose all the hidden layers are also have the same dimensions, and each of the hidden layers are the graph neural network. And the key idea is that we need to restrict the ranges of searching the node neighbors, and this integral can be approximated by the sum of this kernel operation, and VT here is the node embeddings, and you can think that this kernel operation is this is the parameters of your graph neural network, and it is exactly equivalent to the message passing over the graph that mounted on the function space.
Okay, so
yeah.
The graph means that actually each node corresponds to one mesh point in the domain, right?
Yeah, right.
But the mesh is not necessary to be regular mesh. It can be,
right. Yeah, correct. Exactly.
Freely, okay.
Yeah, right. So now
but they assume the graph. I mean, for each layer they share the same graph, or they. But I think they share the same graph.
It has to be. I think it has to be.
Yeah. Otherwise, how do you
graph structure? Yeah, right. So now the adjacency matrix of the graph is the kernel matrix, and the kernel integration is basically message passing. Yeah, that's the GNO, so-called GNO.
Okay.
Yeah. One more thing. I think what I was going to say. Oh yeah. Oh, it's here. Okay. So this is a pipeline of the GNO, and you have this is your input functions, and this is your solution functions, and then you construct the graph by subsampling the function space, and then you learn a graph neural network by message passing. And what if you have a new node? Well, that's why they claim that they can do the super resolution. So if your this is your training graph, and if you want to do the super resolution, and I think they can construct new nodes, then you will have the node embeddings and the new edge embeddings, and then you can predict this one also by message passing. That's how they do the super resolution using the GNO.
It says no interpolation needed, but if you do the message passing, it is an interpolation, right?
I think they don't do the
You just use neighboring nodes to do the interpolation.
Yeah, right. They don't interpolate naively by averaging over these two nodes or using some spline method. They interpolate by message passing. I guess that's
okay. And then there are message passing. Can you take the slide one slide above?
Okay.
So you mean they calculate this integral through message passing?
Mhm.
Am I correct?
I'm sorry, can I say that again?
Because if you do message passing, it's kind of like a loopy propagation, right? You need to repeat this until convergence.
Right.
Okay.
I guess this is a very expensive method.
Yeah, then that means
if you have a new node here, if you have new node here and you connect to its neighbors, now it is not balanced, and you need to rewrite the message passing to achieve its edge embeddings and node embeddings.
Oh, so initially they assign the V values at all the nodes to be the values from the previous layer, and then do this iterative procedure to the message passing through this nonlinear operator.
Yeah, right.
Oh, I see.
Okay. Yeah, that's basically their general work. This is, I think, published 2 years ago at Euribs. And I didn't find this the particular paper for this approximation. The other approximation is called the low-rank neural operator. Well, this is very simple approximation. Basically, you can approximate a kernel, excuse me, by R functions. So let's imagine just consider 1D case, which is the output function. It's just a scalar, which means that the kernel xy, the kxy is also a scalar. Then this is our vector function. This is also, I think that there is a transpose here. This is also a vector function. And then you learn R phi and R psi, the like 2 sets of functions. This is a neural network. This is also a neural network. You can keep 2 separate neural network or just use just one neural network.
This is just feature mapping. This just use neural network to construct feature mapping.
Yeah, this is basically you can represent a kernel function with R in the product functions. And then you can write down the UX, and you can change the order of integral and summation because they are linear. And the phi x is now depending on the differential of y. You can move outside, and then you will arrive this form. This is neural network, but this term is very interesting. It's not depending on S. It's actually a global, it's an inner product of 2 functions. It's not depending on the particular value of X. So you can actually compute it offline and reuse it again and again. And so the complexity of this one is big O RJ.
Is it assuming the dimension of psi j the same as Vy? Is psi j transpose X, psi j Y, right?
Yeah, right. No, I think I'm wrong. So no. I think they are right. I'm wrong. I was wrong. So I think they are. What?
Oh, psi j is still a scalar.
Yeah. So if the kernel is a scalar, then phi should be a scalar function also. It cannot be it's not a vector function.
Okay, okay. Then psi j,
Yeah.
I mean, this notation here is really awkward. So psi j is
Right.
a vector, but psi j evaluated at a bunch of points sampled from D. Yeah.
Yeah, right. So this is a very simple approximation, but it derived there another neural Ips paper called multiple graph neural operator. Basically borrow this idea. We can compose, not exactly decompose the kernel function like this, but we can decompose the kernel function into multi-resolution kernel, the summation over multi-resolution kernels. Let's see what it means. So in their MGNO paper, instead of we sample given function A, we just construct one graph. We construct multiple graphs. Each graph constructed by enforcing different radius, and so the finest graph can capture the short term, well, in spatial domain, in short term relationship, and the coarse graph capture the coarse the long range local spatial relationship. They call this is the multiple method. We will see that immediately. So the key idea, So the key idea is that your kernel can be written as K1, K2 till KL. And so this is your kernel, K, and this kernel are constructed with different graded sizes. So you can see we force R is equal to 4, and by I think this is the this is more like this one. We have a function, and we only consider a certain ranges, but we construct with multiple resolutions. So K1 capture a very local information, and the K2, well, since we grade the spatial domain in a more coarse, by forcing R equal to 4, we can capture more global information. And KL, if we just describe it in 4x4, we can capture entire spatial domain. So they claim that, so this is their motivation, and we can write the kernel at a summation over different resolution kernels.
Okay, but how they design?
Yeah, right.
Which level is,
I'm going to talk about that. So yeah. And now we have K11, K1, K2, KL, but how do we find the connection between them? That's the multiple graph neural network scheme. So let's first look at the formation at behind. Basically, your K11 is just the K11. And the K12, like the K2 here, is written as another kernel function, but also multiply by this. So then your each kernel will have the same dimension. Otherwise, this is 64 by 64. This is maybe a 32 by 32. They are not proper addable. And so if we do this operation, this kernel can be computed numerically. And how this is related visually. So this is your input, or just more generally, this is your VL minus 1, and then your VL, and this is your VL. So the kernel 1 maps map this to this directly, and the kernel 2 map a more coarse resolution, but this more coarse resolution is given by the fine resolution, then transfer it first, and then map to the more coarse this one, and then goes up and then add up. So basically their algorithm will aggregate the information from here to here, from here to here, and from here to here.
Okay.
Yeah. So they develop a V-cycle.
So that means even if you got this coarse level kernel, you still need to calculate this cross kernel.
Yeah, right.
Okay.
Yeah, they develop a V-circle algorithm. Well, to me, it's a very complicated and expensive algorithm, but they say that since L is a hyperparameter predefined, and so this is still a big old RJ linear algorithm. Well, I don't know, maybe. Well, it is linear, but I think it's too expensive. Still too expensive. So that's
similar to the hierarchical H matrix.
Mm-hmm.
Idea is like similar to hierarchical H matrix.
Mm-hmm.
So recently Mike's postdoc has done a job using H matrix to approximate the very large covariance matrix of GP.
Okay.
They kind of use similar structure, but it decomposes in the same way, but the formula is not exactly the same. Okay, let's look at Fourier now.
Yeah, so finally, last approximation, and this is Fourier net, and so it is not magic. We're going to see. So the input is still AX, and the output is still UX, and you have the leafing matrix and the projective matrix. However, for here, each hidden layer neural operator previously approximated by a graph neural network now is computed by a linear, not Fourier operation. And this is your input, the input of your hidden layer. This is your nonlinear activation. Is not important. And basically, this part solves the integral we have previously seen. So this is kx minus ky vy dy, and they resolve this in Fourier form. This is k times f vx. Basically, they do this thing. This is just some local operation. It's not important, just a transformation matrix. And instead of parameterize this kernel, we directly introduce the parameter R, and we just need to do the Fourier transform of the Vx times it, and do a inverse Fourier transform, and add locally, and do a nonlinear activation. That's the Fourier neural operator, basically the Fourier neural.
So to get to the details, so your K is a neural network, and if they want to do the Fourier transform, you're gonna evaluate the neural network output at discretized input, right? like
Yeah.
even space. And also you got VFX. VFX, they do the Fourier transform. I guess it's just discrete Fourier transformation.
Well, for this, you don't need actually a neural network for the kernel, because you just need need to have the model for the Fourier transform form of the kernel. You don't need to. So we don't parameterize the K. No, we parameterize the Fourier transform of K.
Also, they still assume the Fourier transform of K is a neural network, or just the frequency.
It's just a matrix or tensor. They have three. I will talk about later. They have three options of R. You can parameterize directly as just a tensor of matrix or a matrix. You can parameterize that by a neural network, but based on their statement, simply parameterization like a tensor works the best. If you make the R as a neural network, it works worse.
That means they just estimate the frequency. But how do they do the Fourier transform over V? It's a discretized Fourier transform, right?
Yeah, it's just a FFT. V is a discretized or vector valued.
Yeah, V has already been discretized, so they do the FFT, and then they do the inner product, right? And they then do the inverse FFT.
Yeah, right.
Okay.
Yeah. Another good thing about this Fourier neural operator is that you can truncate the frequency components, so it can discard unimportant components of the PDE system. Let me make an example. So I don't think I have a good example here. Yeah, for example, this one. So this is the, I don't know, the initial vorticity of a Navier-Stokes equation. You can see there is a very nasty boundaries in the field. And if you do the Fourier, you cut off the high frequency components, then your solution looks very smooth. So that's another advantage of the Fourier neural operator. And,
that means there are R tensor, they intentionally truncate a lot of elements in R tensor.
Yeah, they only consider, there is another hyperparameter. There is another hyperparameter called Kmax. They only keep. For example, this in this example, Kmax is equal to, we only consider two Fourier components.
That is at the prediction step or the training step.
I think for the training steps also.
For the training step, okay. How do you do that? If they do the training step, that means they do some ReLU.
No, they manually. There is a lot of engineering involved in this in the implementation. So I'm going to talk about later, but we can give a snapshot. So this is their Navier-Stokes kind of the forward pass of their one hidden layer of the Fourier neural operator. You can see first that there is a function. This is your Vx. That there's some batch size. We can just ignore that for now. And then you first do the Fourier transform, which you can already as a native implementation by PyTorch. Then I think they have do some paddings. I think for 2D Fourier nets, the high frequency is residue in the corners if I remember correctly. So basically, I think what they're doing here, I didn't examine very carefully, is zero those components off and only consider the matrix multiplication in those, or this is also high frequency, I'm not sure, and only consider the matrix multiplications for these low frequency components. Then after that,
so they intentionally mask out high frequency parts.
Yeah, right. And then after masking those components of in a Fourier domain, and you do the inverse Fourier transform, and then you return X.
Okay.
Yeah. Okay. Yeah, another good thing about based on their argument is that the Fourier operator can capture the global patterns. So unlike the CNN, you have a fixed filter size, so it can only capture local textures. The Fourier nest capture the patterns in the Fourier domain, so it is global. That's another good thing about the Fourier neural operator. So I was expecting more people to attend this seminar, so I prepared several slides for the Fourier theory, but I think most of us already know this. So I will just quickly go through all these slides. So for Fourier transform, so in order to understand the Fourier transform, first we need to understand what's the basis functions. So what is the orthogonal set of functions? So we have already seen the inner product of two vectors. For example, U transpose V, and this is D by 1 by D. So now, and this is D by 1, and we will resume a scalar. And we define the inner product of two functions. It's like this. If two functions are orthogonal, their inner product is equal to 0. And if we define there is a set of functions, if the set of functions are orthogonal, means that they are pairwise orthogonal. And we can prove that the cosine and the sine functions are a orthogonal function set. So they can be used. We can prove that can simply derived. So basically, the cosine and the sine function can be used as a basis functions. And the Fourier series states that any periodical, this is very important, only periodic function can be expanded as a series of cosine functions. And this is, it has to be periodic function. And we can write it as a series of cosine functions, I can see here. And then we can also expand it as a cosine function, the sine function. And then we can derive, so this is the general form of a Fourier series, has 3 parameters, a naught, an, and a bn. This is a cosine series, and it's a sine series. And you have a closed form, analytical form of the constants. And of course, the problem with this is that this looks really ugly. You have 3 parameters, and by using the Euler theory, we can introduce the complex number, and the Fourier series can be written as this. So yeah. So now we have talked about the Fourier series because only periodic function can be written as a Fourier series. If you have a non-periodic function, like a general function, what do? You just force the the period to infinity, you will have the Fourier transform in this form. So that tells you that if you have a periodical function, no, sorry, this is a periodical function. So basically, it tells you that if you have a periodical function, then your Fourier transform is discrete, because you can represent it as a Fourier series. But if you have a non-periodic function like this, then your Fourier transform is continuous. You have infinite number components of the in the Fourier domain. So yeah. Another good thing about the Fourier transform is like we have discussed, we have already seen. So in so the convolution in the time domain is equivalent to the multiplication, simple multiplication in the Fourier domain. Why that is important? I think this is this kind of not related to this neural operator, but I can say something. Basically, when I was studying control theory and the signal processing, we have a black box, and they have some electronic components, like you have a capacitor, you have a conductor, and you have a resistance. And you want to study what a signal, electronic signal passes, and what is the result signal. And then this signal can be is known, or it could be a black box, or it could be some can be described by a set of differential equations. So the main point is that this function, this system has a response function called GT. Then you will have a FT. Then your result, the output, is the convolution of the system response you need to convolve the system response and your input signal. This is very complicated. So in the signal process, the double E people usually we need to transform this into a Fourier domain, and you have a system, and the system also input transform domain, and this is just equal to Fs times Gs. So basically, we want to this paper used the property of use this property of the Fourier transform. And of course, in real life, your signal cannot be continuous, because you have you cannot input a continuous function into a digital system. So basically, people develop a DFT in general, which is discretized Fourier transform, and a DDFT, which is assume that your Fourier neural components also is discretized, and also FFT. It's a faster Fourier transform, and the faster Fourier transform has the complexity of n log n, and the n is your sampling, the number of your signal samples. And that's a lot of another. And you can also do the 2D Fourier transform, or can also do 2D in 2D space. For example, you have an image, you can decompose it by different frequency. And another property of the 2D Fourier transform is the closest in the center. It means the lower frequency, and when the corners has the highest high frequency components.
So 2D means you have two time axes, because Fourier in the time domain, you already assume is a it's a signal along with time, right? But for 2D case,
no, you don't have time. The Fourier transform does not have to be applied to the time domain. As long as you have a series, you can do the Fourier transform operation.
okay, so here you assume,
Then,
okay, your image has 2 axes.
well, if you have to say, you can say this is xt, and the y is yt. If that helps, if that is helpful. But we don't need to assume that. Just a spatial domain. Spatial domain, you can also decompose the spatial domain in by Fourier transform. Yeah, I think that will be it. Previously, we have this form and want to compute this, but now we directly parameterize this kernel and do the inverse Fourier transform. And now we have the module of we have replaced the graph neural network module by the Fourier module. Now we have already seen this. This is how they implemented code. This is I think this is just a layer class, and this is the forward method of that layer. First, do the Fourier transform, mask out the high frequency component, do the inverse, and return it. And another thing to talk about, I didn't quite capture in that paper, but if we want to use it, we need to carefully with it. So now, theta is the Fourier transform of the kernel. So it is basically a complex numbers. So we need to carefully parameterize our theta in a symmetric way. Means r theta k is equal to r, no, not real number, r phi to its conjugate. So then we will not complex numbers in the kernels. Otherwise, if we don't carefully parameterize the r theta, then there will be complex number in the kernel. That's a
but alpha here are just tensor, right?
Yeah, tensor.
If they are tensor, you estimate? Oh no, alpha tensor. Okay, it's just amplitude. As long as it assumes the amplitude are symmetric, that's fine, right?
Yeah, right.
The frequency is predefined. Oh, another question I want to ask: how do they choose the? So the frequencies themselves are predefined on the whole domain. Right?
Yeah.
So assume the whole domain covers one period.
I'm sorry, say that again.
I mean, they assume the whole domain is covered by just one period, right?
What do you mean the whole domain is covered one period? We don't need to.
Because if you discretize if you did DFT, you're essentially assuming the signal is periodical.
There is a theoretical justification for that, but usually we don't concern about the periodical function constraint in real
like standard frequency is defined. I guess is between minus pi to pi or 0 to pi, and they just do some linear transformation to this domain, right?
Right.
Okay, that's what I mean. That's what I mean.
Okay.
I mean, they are just defined the whole domain with one period.
No. Okay. Yeah. So that's it. That's another thing is that so the Fourier neural operator can only capture the the periodical boundaries by introducing another another W also helps to except to handle have the transform the local information. It can also help to check the non-periodical boundaries. Okay, so here's a summary. So first, they proposed a graph neural operator, which has the approximate this integral by a neural network. It has the complexity of J. J is the true pre-given discretization, and the J prime is the subsample of those discretization. And the low rank is a linear, and what they said. And a multiple graph neural network, even though we have seen that it is a very complex approximation, but the claim still has the linear complexity. And finally, the Fourier neural operator, which has the J log, which is bounded by the fast Fourier transform. So that's yeah. I guess now let's talk about their experiment. So yeah, so this is the general form of the linear operator we have already seen. And so this is your ground truth function. It can be the boundary condition to the solution, or the solutions to solutions. There are 4 PDE systems used in their experiment. 2 are boundary conditions to solutions. 2 of them are solutions to solutions. And this is their define how they define the relative error. And this is the setup for method. They use 1,000 training instance. One training is functions or examples, rule activation. No batch nor is needed, and the 200 testing instances. They for each method they only have 4. They only stack 4 different neural operator modules. Has the latent space of 64, and for 1 dimension, and for 2 dimension problem they have 32. And this is the settings of different methods. And for Fourier method, they keep the maximum components, fragment components to 16 for 1-dimensional problem, and 12 for 2-dimensional problems, which is the Navier-Stokes. I think it's a Navier-Stokes. Yeah, so if you remember, so another view of those kernels are the green function. So unfortunately, for most PDE system, there is we cannot find a green function to solve the PDE. But fortunately, for 1D Poisson equation, the green function has a closed form. They compare the ground truth green function and the kernel that learned by the neural operator. You can see that it's very similar. And the Darcy, this is another boundary condition to solution example called the 2D Darcy flow. And this is the input boundary condition, which is sample from, I don't know what's this, and so some normal, truncate normal maybe. And truncate then take the binary, maybe. This looks like a binary input. And then this is your output solution. And then you can also do super resolution. This is the trained on the 16 by 16 meshes and test on the higher meshes and the arrow.
This is based on, this is the Fourier net result or graph.
This is a Fourier, I think.
Okay.
Yeah. And yeah, this is the numerically they compared several methods like the vanilla neural network, RBM, the reduced base method, fully convolution neural networks. I don't know what that is, and for their variants, the Fourier net achieved this arrow, and yeah, that's very interesting. That reflects their results. Is that this arrow is invariant of the meshes. There are meshes. You can see they increase the resolutions of the solution field, but you can achieve relative constant arrow.
Okay. Yeah, here you can see the dipole net. The dipole net has kind of similar trend.
Yeah.
So I still think they just give the exact solution and just downsample to the mesh.
Yeah, right.
Yeah, interesting to see that the George submitted a paper recently and showing that their dipole net outperforms FNO in every data set. I don't know if they replicate the results in this Darcy experiments.
Okay, that's interesting. And another the Burger's equation invokes time, and I don't know these figures, but the point is that we want to for Burger's equation and Navier-Stokes equation, we want to map the solutions, the current solution or the near future solution to a very long horizon solutions to t equal to 100 something. I think this is their solutions at t times 1 and t equal to 10. This is the experiment results of the Burger's equation, and you can see that they also. Well, I think this
I'll ask Michael to check
okay.
the settings because in their paper they claim the dipole net outperforms FNO in 7 or 8 data sets and settings.
I think this, well, after all, I think these are pretty numbers. Yeah. And yeah, this comes to the most challenging one called the Navier-Stokes equation. There isn't too much C here. We have already C. This is the initial viscosity. It's not the input function. The input function is the target. The input function is the solutions is ux ut equal to 0 to 10, and we want to, for example, take the solution is u, for example, t equal to 15 to 30. That's the kind of mapping for this Navier-Stokes equation. They compare the UNet, TFnet, and the ResNet. I don't know what that is, but they have two variants. So since the Navier-Stokes is a 3D tensor, so we can explicitly take the time step and model it using an RNN. Then your input is a slice of this tensor, or you treat the entire 3D tensor as an image, but has 2 10 channels. So that's where their FNO 3D and FNO 2D is. And you see that for different, I think for verticity, they try different verticities. And you can see that the FNO 3D have, I think.
What does nu mean?
They do is the, I don't know, this is this term. This is the viscosity.
Okay.
Viscosity.
Yeah, it's a parameter of the NS equation.
Yeah, this is also a very promising result. You can see that this UNet, I don't know what's the exact structure of this, but the UNet has like 4 times of parameters than Fourier neural operator 3D, but it achieves much better relative errors than the UNet. And yeah, so there are also some random thoughts, but I'm not sure about that. So the first thought is like the neural or ordinary different equation. Can we use the adjoint method to train the neural operator? You can see the different layers of the FNO are the observations of an ODE, and use the adjoint method to train this Fourier neural operator, exactly like the Ricky Chen in his neural ODE operator does. But I think that's a little bit trivial. And another random thought is, so how do we quantify the uncertainties of this neural operator? For example, given a particular, so for example, this viscosity, and how do we model a probability distributions over this function space, and we will know which initial vorticity or the input function gives the most entropy, for example. Then we can pick it, actively cast the neural operator into the general active learning framework. And I think that's all I have for today.
Okay, great. Any question?
Any questions about this? It's a relatively long presentation. But as long as you understand their key idea, the remaining of their paper are very kind of easy to follow, except there are some mathematical expressions are abused.
So I'm thinking about their R tensor. So one straightforward modification is that you can use some tensor decomposition form to reduce the size of R, because they want to no matter what kind of mesh, they first do some high dimensional, like they map into a high dimensional space, right? Through
Right.
matrix. So you can imagine, do the FFT and IFFT, they're all dealing with a lot of parameters in R. Then I think a straightforward approach to reduce the model parameters is just to, because those these R tensor or R matrix won't be the same for different layers, right?
Yeah.
So you can assume they follow some structure like tensor train or block Tucker, those kind of things, to reduce the number of parameters.
Okay. Yeah, that sounds good.
Any other question? No question. Is this talk hard to understand? Shin, you want to say something?
Yeah. Firstly, I think this talk is a little difficult for me to follow at first because I didn't know the PTE much. I didn't know the background, and but now I have. Actually, I have.
I don't know PDE too much either. It's just a machine learning model. I don't know PDE actually no more than you, maybe. Yeah.
Okay, then I have one question. So for the FNO, for the R, how to is that R predefined?
No, R is not predefined. You can think that R is the weights of Fourier components. You can linear map the Fourier components will be results tensor or matrix R, or you can nonlinear project those Fourier components. Then you can use R as a neural network. That's also fine.
Okay, so why it need that operation? I mean, why it need to do the Fourier transformation and then the inverse? So I didn't get
that. That's a very good. That's a very good question. That can be explained the introduction to the introduction to Furry theory. Basically, the Fourier transform is not new. It's actually studied by those control people. Control theory has a very long theory, like the 18th century to now. There are still some guys. There are still guys to study the control theory. But the control theory says that, okay, so if you have an input signal and you have a system, you want to know what the system respond to that input signal, which will be the output signal. Okay. Yeah, so for example, you have, I don't know how to explain that, but you want to compute the output signal, you need to convolve the input signal to the system response, which is GT here. That's a very, very expensive computation, especially in the past, but we don't have computers. So then people developed the Fourier transform. The Fourier transform, we can transfer the GT and the FT into the Fourier domain. Then we don't need to. You can think that the convolution is like, it's not the convolution that you see in the convolutional CNN. Actually, CNN is a very simple. It's actually just give you the operations, but in here you need to have a window size, and actually not a window size. You need to invert the GT. And in order to compute one style, and you need to convolve the entire input space. That's very expensive. Then people find we can transform those GT and FT into the Fourier domain. Then we can do pointwise multiplication. Then we will have then we transfer those back into the time domain. We will have the exact same results as we do the convolution. That's a very fast way to do the convolution. And the bottleneck of this paper is to do the convolution. So they got the borrowed idea. We can first map the embeddings vectors, the hidden embeddings into a Fourier domain. And then in the Fourier domain, we do pointwise multiplication, then we transfer it back. And we will have the output of the neural operator, which is bottlenecked by the integral.
So basically, one sentence, they just want to efficiently solve the integral. The Fourier transform, inverse transform is just one technique.
Yeah, right. Yeah, previously, okay, so previously you have Mn J square complexity. And Mn is the dimensional of the function space. So it's a constant, you don't need to worry about that too much. So previously we have OJ square complexity. Now we have O n log J log J complexity. Yeah, it's like the bubble sort and the quick sort.
I see.
Okay, any other comments? Okay, great. Yeah, thanks, Shibo. Give
Thank you
a
for listening.
comprehensive talk about this line of work. That's very interesting because last time when I discussed with Michael, he pointed out a recent references called the physics-informed DeepNet. Seems that it's even better than DeepNet, and DeepNet is claiming him to be better than this Fourier net. So we shall discuss about that. But I'm kind of skeptical about the results because all the data sets are kind of selective. Like even for physics-informed neural network, it can now solve even a little bit more challenging problems. I don't believe like if you want to learn an operator, I give you a even better, even more challenging problem. I don't believe you can solve it. So yeah, I mean, at least the linear function operator, the so-called neural operator, is now very appealing. It's a hot topic.
Yeah.
Okay, thanks. I think on Wednesday, June will present the multi-resolution Gaussian process, and on Friday, Xin will introduce the work about neural network pruning.
Okay. Thank you, guys.
Thank you.
Thank you.
Bye. Oh, Shibo, I want to discuss with you for a few minutes.
Okay, sure. Yeah. Right, sure.